Hello and welcome to the next session in our series on intelligence. This is a doctoral consortium series where we're trying to create a global platform for doctoral researchers and young academics across the planet. Today, I'm delighted to have somebody who has played a major role in many of our lives for some time, not an architect, but a computer scientist and a businessman, Stephen Wolfram. In many ways, he needs no introduction, but let me just say something first of all. Oh, sorry. I, uh, I myself have used his book, Wolf, a New Kind of Science, for some time. I was frog marched by Carl Chu after I was teaching at Columbia. He said, "You have to buy this book." And here I'm teaching in YAC in Barcelona. I did tell them that they should invite you to give a lecture there, Stephen, and I think you gave an online lecture. But Stephen has got an extraordinary background. Let me just simply say, I love this shot because it's got these books in the background, and it's great I can see it today with these books in the background because it is Stephen's background that is most astonishing, and particularly the age at which he started to do things. So Stephen's father was a businessman, but also someone who wrote a novel, and his mother was a professor of philosophy at the University of Oxford. But his grandmother was Sybil Wolfram, was a psychoanalyst from the Anna Freud approach towards psychoanalysis. An astonishing background. The family came out of Nazi Germany right just in time, and Stephen himself was a prodigy. At an astonishing early age, he was doing remarkable things. He first went to Eton, left early, and he then went to Caltech. And by some improbable way, I'm not quite sure exactly what the age was. By the age of 20, I think it was, Stephen had got a PhD from Caltech. So, what a meteoric beginning with an incredible background. And I think the reason why I like this particular photograph with the books in the background is that Stephen is one of the few computer scientists who writes books. I guess this comes from your background, Stephen. And then I guess in some senses, the rest is history. One of the most important things, of course, was this book, a New Kind of Science. But there are all these other enterprises, Wolfram Alpha, Mathematica, Wolfram Physics, and so on. And the legacy, in fact, of Stephen's work can be found. Probably he's not aware of it himself because he's had an incredible impact. This is the work of Philippe Morel, who is with us at the moment, who has been using Mathematica. Philippe runs a computation and architecture master's program at UCL Bartlett that has been voted the top school of architecture in the world for the last 2 years. And also from the Bartlett, we have Alberto Fernandez, who himself actually is from Chile. So Philippe is from France, and Alberto is from Chile. So the impact, this is going to be today something of an interview or a discussion, a fireside chat, should we put it that way, in which I'm going to start off with some of the questions, and then we're going to invite Philippe and Alberto and Bhavlin Kaur, some of the many sort of architectural researchers who've been using Stephen's work to inform their own project. So let me start by unsharing my screen and welcoming Stephen to Digital Futures.
Stephen,
Stephen, I just wonder if you could say something, because whenever I was introducing you to my students in the past, your extraordinary background was something that I never got far beyond that because it was so extraordinary. You had a prodigious beginning. You were extremely very young when you started off, and you come from an astonishing background in terms of your parents and your grandmother in particular. Do you want to say something about that background and how that
I don't know. I think I have been, I don't know whether it's luck or kind of intention, but somehow I've managed to kind of alternate between doing sort of basic science that's quite abstract and intellectual and developing technology. And I've kind of done that alternation about 5 times so far in my life. And it's turned out to be a really powerful thing because you do a bunch of basic science, you figure out a bunch of conceptual kinds of things that tells you what kind of technology you can build. Then you build a bunch of technology that provides tools that then let you get to kind of the next level up in kind of conceptual thinking. I mean, I have to say that quite a lot of what I've done in recent years has been kind of one can think of it as kind of philosophical in nature, although I think of it as science finally being able to solve problems in philosophy. But one feature of my background and my mother being a philosophy professor was that when I was a kid, one of the things I would always say is, if there's one thing I'll never do when I'm grown up, it's philosophy, because people have been arguing about the same things for 2,000 years or whatever. The really neat thing is that now I think from unexpectedly, a bunch of the science that I've been able to do actually starts to actually tell one things about those questions that people have been arguing about for a couple of thousand years, about sort of, what is the universe made of? What, how do we think about kind of the way that we navigate and sort of whether we have free will about how we interact with the universe and so on. But actually, I'll come. Maybe I can launch into one thing that I've found interesting, which is this sort of question. Maybe we can of one of the issues is how do you deal with understanding things that are very abstract? What is the best way for us humans to ingest the very abstract? And I think the thing I've often found is that kind of visualization, using our eyes are the kind of highest bandwidth mechanism we have to get stuff into our minds. And so a lot of the things I've done have been made possible because we've been able to, visualize things, take the abstract and make those things things that we can sort of appreciate visually. And I guess one of the side effects of that is that we go from these very conceptual kind of foundational things to kind of visual forms. And then the obvious question arises, how can we kind of make use of those visual forms for things that we want to, in your world, actually build and live in, so to speak. And I guess one of the things I've sort of found interesting is I think we have managed to understand from thinking about, simple programs, the computational universe, we'll probably talk about all of these things. We've understood a little bit about sort of the essence of how nature makes the kinds of forms it makes. But yet, because we've gone to this sort of foundational level, we have something which, in a sense, generalizes nature. And that gives us a way to sort of produce form in a way that is kind of familiar in the sense that it is the kind of thing we have seen in nature, but yet general. And I think that's, I'm very curious about how that relates to, how we, if we're embedded in these kinds of forms, how do we interact with these types of things? I mean, I will say that just on the kind of science direction, one of the things that's happened in recent years is, my science has gone through several different stages, and the thing that is most notable in recent times has been that the emphasis on kind of the observer and how it is that we perceive things, what is there versus what we perceive. And I've now kind of, one of the excitements of recent times has been kind of, I think, understanding a lot about the way that the physical universe is set up and the sort of necessity of the laws of physics that we have based on kind of the laws of physics that we have are based on the way that we can perceive things. They're based on sort of the nature that we have as observers. So that's kind of my the kind of arc of things has been well, I was sort of lucky that I started off involved in physics at a time when physics was in a very energetic state, and then did many things with computation, and then have come back to physics. And the fact that I kind of know the physics that already got done is very useful if you want to take the next step. So that was a long, brief introduction.
No, no, that was very useful. I think what fascinated a lot of architects around the time that a new kind of science came out was not just the work that you were doing with cellular automata, but also the other work that was coming out of the Santa Fe Institute and so on swarm intelligence and those things. The idea that complexity could emerge from simple rules. And that, in some senses, is something that's been followed through. But I guess, I mean, were you aware at the time that maybe your work was being taken up by architects, designers, and others in other fields
I found it out quite quickly, yes. No, I mean, one of the things that was nice is that if you look at different fields and you look at kind of their absorption rate of new ideas, somehow I think in things like the arts and architecture, there's actually a faster absorption rate than there is in a lot of science. I think that it's kind of there is more of a recognition of kind of the new, and it's also more obvious that something is happening, so to speak. I think that some areas of science, it's like we have a methodology, and that's what we've been using for the last 100 years, and that's what we're going to go on using. And I think yes, I was aware of this, and I even did a couple of years after the New Kind of Science book came out. I did a bit of a tour of architecture departments that was quite fun. And then occasionally I've seen different kinds of objects where I can plainly see this is something based on kinds of rules that I've worked on. Most dramatic is a train station in was the recent thing near Cambridge, which has a big metal. I haven't seen it in person yet. I'm actually going to see it in a few weeks in person for the first time. It's got a lovely kind of metal it's sort of encased in this metal structure, which has a high resolution version of one of my favorite simple rules that does complicated things, Rule 30. And it's but that's just one that's more of an ornamental example. I mean, I think that from what I could tell, there's a certain amount of I mean, I don't know how one thinks about ornament, but it seems like ornament is, it goes from, I mean, okay, so now I'm going to jump into an area I know little about, but this is a sort of my I'm curious, when we think about how do you make sort of forms that people feel like living in, so to speak, you might say, well, all we really need is a box. And turns out people don't, I think, particularly like mostly pure boxes. And the question is, well, what are people going to like? And it seems like things like ornamenting things is something which helps, I think. Again, you guys are the experts on this, so you can, that sort of helps in humanizing the experience of things. And the question then is, what is, what is it about that process that has how do we feel comfortable in things, and how much does that relate to what we are used to seeing in nature, and how much of what we see in nature, what is the essence of what we are taking from nature, so to speak? Is it and so so I'm curious what the view from people who actually do this, so to speak, might be. But yeah, I was um I was it has been over the years, there are all sorts of different examples where it's been really cool to see these kind of sort of forms based on simple rules ending up being used. The thing that I always feel about this is the reason this works or can work is that because underneath there is a simple rule, there is some kind of logic to there's some kind of logic that we can perceive. It all sort of makes sense. But yet, the surprising fact is that even very simple rules can produce very complicated behavior. And that means that it isn't just sort of, plain and simple. It can be very elaborate, very engaging, so to speak, something where you kind of, as you look at it, you wonder what's going on here. And it isn't just random, it has a logic to it, but yet that logic is, that there's an elaboration of that logic. You can sense that there is a logic underneath, but yet there's also a certain richness to the form that is engaging, in the sense that you don't just look at it and say, oh, I know what this is immediately. It's something that engages one. At least that's my very, very amateur view of kind of how one might think about these kinds of things.
One of the things that's, of course, has been one of the issues of our time right now is the advent of AI, or the explosion of AI, shall we say? And you've been kind of involved in that in indirect ways. I think that some of your tools have been incorporated into ChatGPT, but there's some bigger questions that are now being postulated, and maybe speculative questions that seem to somehow back up some of your early theories. I was listening to Blaise Aguiriakos, who has a book coming out this week, in which he's basically saying that life is computational, which seems to be in some many ways to echo some of the thinking that went into a new kind of science. What would you like to do? I mean, it's and I guess like me, you might have been brought up with a Hitchhiker's Guide to the Galaxy story, where the world itself is seen as a computation, as a computer. So in many ways, your early thinking has been validated by recent discoveries. Do you want to comment maybe on some of those?
Yeah, I mean, there's a question of why do neural nets work? Why is it possible to make ChatGPT? I wrote a little book about this actually soon after ChatGPT came out because I was so fed up with people asking me how does it work. I thought I should just write it down, and I've been then a little bit shocked that how widely that particular account has been read, and really it's I think still about the only account of sort of why these things work. And I think the thing to understand is that the one of the things about why does ChatGPT work? Why are we able to get kind of human-like essays coming out of this kind of system? I think the number one reason is because human-like essays have more structure than we knew was there. We have been very familiar with the fact that in a language like English, a typical sentence is constructed as kind of noun, verb, noun. But yet our standard grammar hasn't talked about which noun, which verb, which noun. I think what happened is, in effect, in the training of an LLM, we learnt a bunch of additional rules about kind of what goes with what. And it turns out that when you string together sort of what goes with what with enough kind of enough sort of knowledge of how that's set up at a semantic level, that it's not so difficult to get what seems like a kind of human reasonable piece of piece of text. I think so. In other words, the things that we are doing that sort of are kind of our way of producing things have rules that we didn't know were there. My guess is the same is true in a kind of visual and spatial sense, that there are kind of more rules. There are things where people will say, yeah, that looks like a nice piece of graphic design or something like this. And implicitly, we have certain rules for how, and sometimes people try and make these a bit explicit. But my guess is that, we are creatures that, in which the things we do are governed more by kind of rules which are implicit to us. Now, in terms of this whole question about what is going on in an LLM, why is it working, how can it do what it does? I think the thing to realize is if you say, okay, distinguish a picture of a cat from a picture of a dog, you say, what is the mathematical definition of what's a cat and what's a dog? Well, nobody has that. It's just humans will say this is a cat or this is a dog. And the big surprise is that neural nets make that distinction in a similar kind of way to the way that humans do it. They'll say there's a cat, there's a dog, and just like humans will say that. And I think why does that happen? It happens, I think, because the fundamental architecture of a neural net is similar enough to the architecture of our brains that we basically get agreement about kind of the distinctions that we make. So in other words, the reason the neural net is working is because it's kind of a simple version of what's happening in our brains. Actually, it's probably a closer approximation to what's happening in our brains than we might like to admit. I mean, it's the same kind of phenomenon as the fact that even though the detailed hardware is different, still the functionality is similar. And that's the same as what we see in computers, where we can have different detailed hardware, but yet the ultimate computations that are done are similar. But I think, there's a question then of questions like, okay, so if it's doing all this clever kind of thinking like stuff, can we look inside and see how it worked? And I think the answer to that is a fundamental no. And one of the things I was doing recently was trying to make sort of a foundational model for what happens in machine learning. And this turns out to be something, one does machine learning all the time, but one has never known why it works. And okay, there's a slightly long story, but I think an interesting one relates also to life. So something I had tried in the 1980s was to take these programs with simple rules and to say, let me consider changing the rules and seeing how that changes the output, and maybe doing something like natural selection on the rules to be able to select an output that has some particular characteristics. I tried doing that. I didn't push it hard enough. I never managed to make it work. I came back to that last year, now knowing that machine learning works. And one of the big discoveries of a decade or so ago was if you sort of bash one of these neural nets hard enough, it will learn stuff. It wasn't clear that, if you bash it a billion times, it didn't learn anything, but you bash it a trillion times, it does learn something. So came back to this and discovered that even with these simple cellular automata, for example, just arrays of cells with simple rules, that you could do adaptive evolution, and that adaptive evolution is remarkably powerful, and that you end up getting these very elaborate forms where you say, I want this thing that lives as long as possible, but not forever, for example, or I want this thing that makes such and such a kind of shape. And maybe we can look at some of these pictures, but what ends up happening is that the adapting the cellular automaton rule, which is kind of like the rule is kind of like the genome of an organism, adapting that genome, the phenotype, the actual form that is produced, varies a lot, and it is you can successfully adapt to a very wide range of fitness criteria. So you can get all these different things that have some overall shape, for example, but then you say, well, how did it do that? And you look inside, and it's this incredibly complicated pattern. It's a pattern that, rather interestingly, looks very organic. There's something about it that kind of reminds one of life. And so what we're finding is we don't yet know, something's still trying to be figured out, what is the range of kinds of things that you can adapt to? If you say, oh, I want this thing that has this and this and this and this and this characteristic, you might not be able to get that. But at least within some range of kind of fairly simple to describe characteristics, you can get those things. But the way you get them are these very elaborate kind of patterns of behavior. They're not things where you can go in and say, I know what's happening there. I can just explain that this does that and so on. It's something where, there's a bunch of bits and they just come together to do the thing that you asked, you adapted them to do. So I think this is fundamentally how biology works. We see all these things that we identify as very complex forms in biology. They're complex forms because that's how biology happened to be able to solve this problem. And if history had been different, it would have chosen a different solution, so to speak. And one of the things that's kind of a charming thing you can do is take one of these complicated patterns and ask an LLM to describe that pattern. And the descriptions it gives are shockingly similar to the kinds of descriptions that you'll find in biology textbooks about how biological systems work. So I think that the way I like to think about this is you have these simple rules, and the question is, can you predict what these rules are going to do? And the thing that is sort of one of the big discoveries that I made back in the 80s is that there's this phenomenon of computational irreducibility, that even though you know the rules, to figure out what they will do, you might have to do an irreducible amount of computation. You might effectively have to follow each step of the rule to see what happens. You won't be able to kind of jump ahead and say, oh, I know that that's just governed by this formula. So the computational irreducibility, I think what we see in biology is we are kind of these lumps of frozen computational irreducibility that happen to achieve certain fitness criteria. I think in machine learning, it's the same thing. What you see as the result of training a machine learning system is sort of the entrainment of certain lumps of computational irreducibility. And so when you look inside the machine learning system and you say, why did it do that? How did it work? It's just, well, there's this lump of irreducible computation that happened to achieve this particular function, but there's no explanation. There's no kind of narrative that you can give about why it worked that way. It's just, this is a piece of irreducible computation that happened to do this particular thing. So, and one of the things that I think is interesting about life, I used to think that life was sort of just another example of generic computation. I have increasingly come to realize that there's actually a little bit more to it, that life is kind of one of the features of life, and something we discover from the recent decades of molecular biology is everything is orchestrated. We used to think of, life as about biochemistry and chemical processes and just a bunch of molecules sort of bouncing around randomly. and making the things that we are. But that doesn't seem to be what actually happens. What actually happens is that these molecules are, they are orchestrated. One molecule, moves down another one. It has some little mechanism. At a small scale, there's a lot of simple rules going on. At a large scale, that produces this sort of elaborate forms of biological organisms. But I think that one of the things I'm currently chasing is kind of a theory of what we can call bulk orchestration. When you have a large number of these component parts, which are somehow all orchestrated together, and I think that is something that happens as a result of this sort of overall adaptive evolution. I mean, it's kind of like from the rules, you have this sort of rules at the bottom that are working up to produce kind of the behavior we see. And yet there is also sort of a downward thing that's happening of this sort of overall, is the organism going to die? Or, is it going to be a fitter organism? There's this kind of downward pressure from adaptation. And I think that there's sort of a thing that results from having sort of a coarse way of doing that fitness that sort of affects the intermediate zone of what these simple rules produce. So I can't tell the end of that story because I haven't figured it out yet. But that's a thing that I'm kind of suspecting that there are some very generic things that can be said about kind of living systems that have been subject to certain kinds of adaptive forces that can be said that it doesn't matter what the adaptive forces are. It just matters that there were adaptive forces and that things started from simple underlying rules. So that's a coming attraction. I haven't figured that part out yet.
It sounds like emergence is coming back with a vengeance to come and to be a driving way of explaining a lot of things. Let me just simply say, Stephen, that I'm one of those people who bought a copy of your book about ChatGPT. And in my book, this is about the latest version, which is the second edition of a book. It's called Architecture in the Age of Artificial Intelligence, the first book on AI and architecture in English to be published. And I refer to you in this book. So you appear in a book on architecture. And what I was interested in was really your comments about language. Perhaps what ChatGPT is telling us is that language is a bit more straightforward than we thought. And the question that I was going to ask, which you've already half answered in some sense, is that could we apply similar logics to, let's say, Midjourney and those diffusion models, which are generating images?
I think,
Yeah.
yeah. No, I'm guessing so. I mean, one of the things I was looked at one point that I sort of found interesting was if you look at a generative AI image generation system and you say you take the concept of a cat, and the concept of a cat sort of internal to that system is a vector of numbers, and that's and then you say, okay, given that specific vector of numbers, the stable diffusion system or whatever will generate a picture of a cat. Now vary those numbers a bit. What do you get? Well, what you get is something, as you vary the numbers just a tiny bit, you get a thing that is sort of recognizably cat-like. As you go a bit further, you get things that are very bizarre looking. And one of the things that I was sort of interested in is how big is interconcept space, so to speak. In other words, there are places where there are, where we get pictures that correspond to things that we can describe, that we have words for them. And then there's a huge space in between those pictures where we don't have words for these things. And so, one of the things I've been sort of interested in is as you go through sort of human history, there are more things for which we have words. Like one thing I found very striking is nested patterns, fractal patterns, and so on. I think the first examples of that being sort of used were in the 1200s by some mosaic layers based in Italy. But one of the things I noticed years ago is you look at the art history books that were written before people talked about fractals in the late 20th century, and they just have nothing to say about these nested patterns. They just gloss over them. They talk about the images of lions and the mosaics and things like this. But yet, when there starts to be a word, there starts to be something that we are familiar with, about nested patterns, then people start mentioning that. And so my question, in interconcept space, we are gradually, over the course of human history, so to speak, we're gradually kind of putting flags down in interconcept space and putting concepts there and having them be things that become sort of familiar visual forms to us and for which we then have words and can talk about those things. And I suppose, I'm wondering to what extent we can map kind of the history of human kind of form generation into sort of the expansion into interconcept space. And how much does that reflect? I mean, just like we know in, let's say in mathematics, we are gradually exploring a bigger and bigger part of the space of all possible theorems. So in visual form, we could imagine that we are gradually exploring a bigger and bigger part of this kind of interconcept space. But I think this question of what counts as a form that we think is kind of a recognizable, reasonable form is. But by the way, I should say this whole idea of interconcept space also applies to textual data. But related to my point about visualization being the best way that we can get from sort of conceptual issues to things that we can deal with in our minds, it's much harder to say, well, what happens if we make these small changes to things that generate text? Because the text at first just seems to us like nonsense. Maybe at some point this will be some poetic, form that we recognize. But in first instance, text generated that isn't quite text that is the way that we expect text to be just doesn't work out at all. Whereas visually, it's much easier to get things which are sort of distorted versions of what we're used to, and we still can see something there. And somehow then the question is, does that form become familiar to us? Then the question is, given the forms that are currently familiar to us, to what extent can we generate more form that is like the forms we've seen before? And I'm quite certain that there's a kind of an effect. People have looked at this in simple ways for a long time of sort of a visual grammar of forms that are the things that are familiar to us humans. It is not the space of all possible forms, nor is it the space of all possible, even forms that can be generated by simple rules, not even the space of forms that are sort of, in a sense, reasonable based on the way that our visual perception works. I mean, one of the things that happens if you look at kind of, if you vary the, move around an embedding space or something to look at the things that aren't cats but are something else, you are not getting things that are just random arrays of pixels. You're still getting things that have all kinds of structure because that's what the nature of that kind of space of image generation looks like. But many of those things you get are structures that are pretty alien to us. They don't seem to be, and so there's a question of sort of when are the structures, in interconcept space, how, what's the subspace of interconcept space that consists of forms that will be comfortably familiar to us? And how do we characterize that? And is there a way of characterizing that space of comfortably familiar forms using rules that we can write down and so on? So, I mean, I don't know the answers to these questions. I mean, it might be useful to put up some actual pictures of some of these things.
Yes, no, I was exactly. No, that was fascinating, Stephen. Thank you. We've got Philippe Morel here and Alberto Fernandez, and maybe I could invite Philippe, who is very familiar. Well, everyone's familiar with the work, but maybe Philippe to come to maybe show some of the work that he's been doing and just take this argument, this discussion further. Philippe is he's French. He lives in Athens and he teaches in London. Philippe, welcome. You.
Yeah, thanks a lot. Thanks a lot, Neil. As I said before, it's really an honor to be there with you, with Stephen Wolfram, whose work I know really well, obviously, and I'm a long-time user of Mathematica. But let me quickly explain why, in a sense, I'm such a long-time user of Mathematica. So let me share my screen. I think now you should see my screen in full screen mode. Let me know if it
Yes.
doesn't work.
Yep. Yep. Yes.
Perfect. So basically, first of all, let me start with a very quick remark. Stephen mentioned the fact that we can use cellular automata or things he worked on for different purposes, including obviously like decorative or ornamental patterns. In the past, with some of our students in 2012 in London, we chose a slightly different path and we used complex cellular automata. We let's say engineered them in order to create different kinds of structural strengths in materials. We also, for that, made use at a tiny scale of advanced 3D printers, which allows to print with different kind of materials at once, different strengths. And Min-Soo Kim, who was at that time a student from South Korea, came with a small prototype of a bridge, taking into account many different constraints, including wind, etc., etc., and he computed the material distribution in a completely discrete way by using cellular automata and this kind of methods. So I think the work of Stephen obviously goes much further in the discipline of architecture than just being used for ornamental purpose. And it's obviously something I'm very interested in. As you know, architecture didn't evolve that much in the past, let's say conceptually speaking, in the 400 years. The Great Revolution was obviously during the Renaissance at the Quattrocento with the invention of perspective. And when you look at what was taught in architecture school, including at the end of the 1990s, so the very end of the last centuries, it was still based on that. I mean, obviously the shapes, the curves became a bit more complex, but the conceptual basis for this architecture has been invented 500 years before that, during the Renaissance. But at the same time, in the real world, the real world was about that. I mean, when we look at a bank office or an hedge fund management office, it looked like this in the 90s. So obviously there was a big discrepancy between architecture, the discipline of architecture, which was still based on a rationalist, let's say, paradigm. And what personally I understood, also thanks, by the way, to the reading of Stephen Wolfram, of Ed Fredkin, and many other digital physicists or digital let's say, philosophers, because sometimes it's really at the border between pure physics and a kind of almost metaphysics, obviously. So we entered this domain of computationalism, and obviously this is what Stephen has promoted, if I'm right, for a very long time, and this is why Mathematica became so important. So when I discovered that, basically at the very beginning of 2000, this is the kind of tools I was using. In 2000, this is how the interface of a very popular software in architecture, which is called Rhinoceros, look like. So hundreds of icons, hundreds of tools, but nobody had any idea of what was behind, in a sense. And obviously, if you look for the first principle of this, it was completely opaque, and the student didn't develop any mathematical knowledge and mathematical thinking about that. And then I discovered Mathematica, thanks to a mathematics professor at the university, Marie-Vonne Tessier, who was also a long-time Mathematica user in Paris. And suddenly it was a revolution for me because it was like a new birth, because it was a blank sheet. And at some point, if you don't understand the concept, you are not going to do a lot, at least for architecture. Obviously, Mathematica is also, and it's a kind of dual nature, because you can do a lot without knowing, but if you want to do really good stuff, it encourages you to learn by doing, by the way. And on a conceptual level, it's clear that the computer is based on a strong evolution towards the understanding of what is universal in the world. It's a long-term trend in history. If you read Stephen, you see that he was interested very early on the computational power of universal cellular automata. If you look at some other theoretician in the history of computing, like Boole or Whitehead or Shannon, obviously it's all about universality. And you can even see this in the neural network. I mean, in the universal approximation capabilities of neural network, but obviously it's a different paradigm because here we don't speak about discrete things. But okay, let's not go into the detail further. But basically, I was interested on a conceptual level in what is general in architecture, what is general in knowledge as a whole, and what is universal in the world we are living in. And this universality, I find it fascinating on a formal level, obviously, by making use of tiny discrete structures known as voxel, for example. But I also understood this universality as something which had a lot to do with formal languages, because the formal languages, the basis, let's say, of formal languages, for example, lambda calculus has a lot to do, or let's say, is all about universality. I mean, trying to understand the universality of computation and what is universal in languages at some point, without making such a difference between mathematical languages and natural languages. And I think this is something also very interesting. So I started to teach Mathematica to myself to learn. I started to teach Mathematica to my student. I took part of the organization of different events, including the Mathematica Symposium in 2006 in France, in Avignon. I even designed the poster, as you can see here. And I made a link with the discipline of architecture, because one of the pioneers in computer interface, Ivan Sutherland, that all of us knows, obviously, spent a lot of time trying to bring on the table the fact that tools are extremely important in shaping what we are doing as architects. So for me, going back to the roots, I mean, first to Mathematica, and then only afterwards, I discovered that Mathematica has a long story coming from SMP. By the way, the very SMP, I mean, symbolic manipulation program, was very much in line with what I was interested in, because I was interested in this conceptual power of symbol. And then understanding that Mathematica allows students to do quantum mechanics or quantum physics if you are knowledgeable enough, but you can also teach the fundamentals of programming or even graphic design to architecture students. For me, it was the perfect tool. And again, it's not because it was fancy, it's not because it was fashionable, it's not even because the cellular automata became mainstream, aesthetically speaking. It's really because the generality of of this technical computing or scientific computing system was very much in line conceptually with the kind of generality I was looking for in my architectural work. And what is interesting is that when you look at what's happening today, this kind of generality that we see with ChatGPT, because we know that we can ask more or less anything to ChatGPT, but now we know that, for example, it's also used to drive driverless, autonomous cars. And it turns out that using ChatGPT is quite good in helping us to drive autonomous car, which is kind of insane, which also means that probably ChatGPT is catching some of the universality of the underlying structure of more or less everything we are doing. I think I saw also in the work of Stephen when the natural language input was introduced in the system with a double equal, creating this possibility of inputting things in natural language. I think this was a very deep, let's say, anticipation by Stephen of what would happen many years later with artificial intelligence systems, with LLMs as we know them today. Now, just very quickly, here are some images of works that were entirely made by making use of Mathematica. So we can do set design work. This was presented in Banff, by the way. I think it was in 2004. It was a pattern for an exhibition at the Centre Pompidou, a famous exhibition who was entitled Non-Standard Architecture by Frédéric Miguero. This was my diploma work. It was a computational essay. By using this word computational essay, I'm quoting Stephen because I didn't call it like that myself. I discovered this word, computational essay, afterwards only. But clearly it was a computational essay because it was a work which was articulating some philosophical questions with purely mathematical research and investigations on the nature of the geometry we are using in contemporary architecture, things dedicated to curvature, to patternings and things like that. I was mostly interested in a very practical aspect, trying to find some highly developable patterns for the construct in order to make the unfolding of surfaces, you know, these kind of complex surfaces that you have in the architecture of Frank Gehry, for example. I was very much interested in trying to find some logical unfolding pattern. And I came up with an iso-Gaussian unfolding pattern, which is naturally adaptative. So the more curvature, the more Gaussian curvature you have, the smaller the patches are. So yeah, I was interested in this. So it was really a computational essay. It was something bringing philosophical concerns with the issue of surface in contemporary architecture, but also some larger mathematical questions. I use Mathematica also to develop things about perception. How do we perceive shapes? What is the influence of patterns on the perception of shapes? But also sometimes using Mathematica in order to do real structural engineering with some of my students and interns. For example, this is all done in Mathematica. It's a topologically optimized structures. And then later on, it has been fabricating by using a robot, 3D printing, a fully recyclable clay mold in which we poured some concrete, and then we just removed the mold with water, and then we can reuse it as many times as possible. And it even became the let's say the starting point of a startup venture, which is now living its own life in large scale 3D printing. So basically, we can do also graphic design. We can do many things like this. So basically, I made Mathematica my favorite platform. First of all, because conceptually speaking, I think it helps a lot in understanding and catching one of the most fundamental questions I'm interested in, which is the universality of mathematics, the universality of some specific mathematical models, and how this relates to the discipline of architecture at large. So yeah, this is it.
It's beautiful. It's really beautiful. It's very people like me who spend a lot of their time building tools. It's it's wonderful to see the kinds of things that people can do with those tools. It's quite thrilling, actually. But I mean, to make a few comments. I mean, in you know, in the practicality of things that we've built in recent years, you know, we put a lot of emphasis on computational geometry, and I think we've now you know, actually coming in a new version is being able to do computational geometry with more complex shapes. But there's that's one thing. The other thing is doing finite element analysis, which I suspect is relevant for some of the things that you're doing there. But
Right.
I mean, this is you know, I guess I'm I'm curious. I mean, okay, so just to say how I think about, you know, Mathematica, what we typically call Wolfram Language, as sort of the generalization of that versus kind of simple computational rules. What's the relationship of these things? I mean, I see it as being there's this kind of ocean of computational possibility that exists from all the possible rules you could imagine using to compute things. And much of that ocean, so to speak, is um, is not has never been populated by us humans. We don't, you know, it's something that is very unfamiliar to us. We can kind of jump out into the computational universe, start making patterns that aren't like anything we've ever seen before. That's kind of, you know, there's this sort of ocean of computational possibility. I see the main role of Mathematica and Wolfram Language as being to provide sort of a parameterization of that ocean of possibility in a form that we humans can understand, so to speak. In other words, I see it as being this bridge between what is computationally possible and what we can kind of conceptualize with our minds. I mean, I see it as being, in a sense, a notation for the kind of computation that we humans are interested in doing. Just like mathematical notation is sort of a notation for mathematical concepts that we're interested in, so our language, our sort of computational language, is an attempt to represent those things that we can think about computationally about the world in a way that is sort of convenient for us to think in terms of. So, I mean, for me, and I suspect for you too, the you know, one can conceptualize things directly in Mathematica. You know, I can start typing code long before I can explain to somebody what I'm about to do. It provides this kind of medium for kind of thinking about things computationally. And you know, I think that the what we're really trying to do is emphasize things that are sort of accessible to us humans. There is this sort of ocean of possibility out there that isn't quite so accessible to us humans. We can kind of sample pieces of it. And I think one of the things that is really interesting is, you know, there's the part that we understand, and there's the part that's sort of just out there computationally. And as we kind of we're slowly able to explore more pieces of what's out there computationally. And I think that's, when we see like the picture you have here, there's a certain complexity to that, which is not easy to explain with the kinds of narrative explanations that we're used to. It's a thing that sort of comes from the computational universe, but it is close enough to things that we kind of are familiar with, that we kind of, we can resonate with it. At least that's the way I tend to think about it. I mean, I think that I will say, just as a practical matter, that about 6 years ago now, kind of made these big breakthroughs in fundamental physics, which allow us to know, I think, something which is kind of what space really is. I mean, I think a lot of what one's interested in, for example, architectural practice, is doing things with space. What we think of space really as being is at a scale just so unbelievably far below, human perception, that there's no direct relevance to the fact that to what we think space is at a scale of, 10 to the minus 100 meters. That's not relevant for building a building, but it's nevertheless, I think, conceptually and philosophically interesting that we think we now have a pretty good idea of what space fundamentally is, and it really is at some level a network. Instead of, we have thought about space in a very Euclidean kind of way of kind of we just get to say, oh, you can put points in this background of space, and we can label them with coordinates and things like this, and we can have number lines sort of going across space, and we can kind of label pieces of space by real numbers. What we're pretty sure is really going on at the smallest scale in our physical universe is that there are just these discrete things we can think of as atoms of space, and all that there really is the connectivity of those atoms of space, and that the whole structure of kind of the universe and space-time and so on is formed from this kind of very large-scale version of this kind of network of atoms of space. I mean, it's kind of similar to what we see in, like, say, fluid dynamics, where at the smallest scale, we've got a bunch of molecules, discrete molecules bouncing around, but then on a large scale, we perceive this continuous fluid. It's the same thing, I think, with physical space. One reason I mention this is that the actual forms that you get by looking at the structure of this underlying hypergraph, as it turns out to be, that represents kind of the structure of space, those forms are quite interesting. I mean, all that we really know about those forms is their connectivity information. To render them in a way that we can perceive them, we have to, lay out the graph in a sort of arbitrary human way. But I just mentioned this as a kind of an area of form that is sort of is even more a frontier than the forms that we get when we fix space. Like in a cellular automaton, we've said, okay, we're going to divide space into these pixel-like boxes, and then we're going to have structure that emerges from sort of the relationship of these boxes. But we fixed the structure of space. Whereas in what we think is going on in the foundations of physics, the structure of space is itself dynamic. Even things like the dimensionality of space. We're familiar with our own our perception of the universe is it's three-dimensional, but in our models, dimension becomes a dynamical parameter, and probably in the evolution of the universe, there have been fluctuations in dimension and so on, which is a whole interesting sort of direction in physics. But I just mentioned that as something that is perhaps of interest in these kinds of directions. I think, but please, yes.
No, maybe I have a quick question, because I mentioned, obviously we know you are interested in, let's say, the discrete nature of the world. Most probably, even if we all know that at the very moment it can only almost, by definition, or let's say as a matter of fact, remain a metaphysical hypothesis, or at least an hypothesis, maybe not metaphysical, but it's a working hypothesis, since we don't have, let's say, ultimate proofs coming from physics at the very moment, even if we have quantum physics and a lot of indications that would let us believes that the world is discrete. It's not something that can be verified
Well, this,
with absolute
right.
certainty, because that's the nature of the history of science, let's say. It's almost a Popper related problem. We can falsify things, but we can never really verify them.
I think
But
maybe the history is
yeah, yes,
just to and then the history is kind of interesting because people in antiquity lots of debate, is the universe discrete or continuous?
right,
One didn't know the answer to that until the end of the 19th century. End of the 19th century, turned out molecules were big enough that the apparatus that one had at that time could basically see their direct effects. And we saw Brownian motion, things like this. Okay, matter is discrete. Light, similarly, could be thought of as discrete. In the early part of the 20th century, first few decades of the 20th century, if you'd polled physicists, they would have said, oh yeah, space will turn out to be discrete as well. But there turned out to be specific mathematical issues with the way that relativity works and so on, where people said, oh, we can't see how this works. Now, people were lucky at the beginning of the 20th century. Molecules were big enough, photons were sort of energetic enough, you could actually detect them. We don't know yet, and this is a big area of effort, is can we see the discreteness of space? Is there some effect like Brownian motion? One of the things that's sort of interesting about Brownian motion, it was discovered in 1827. So for most of the 19th century, one could have known that matter was discrete, but nobody put, the pieces together. So it's quite possible that we already have experiments that plainly show the discreteness of space, but we don't know that for sure yet. So it is quite true that we don't have the definitive experiment, the thing like Brownian motion for the structure of physical space. But it's worth kind of contextualizing. It's not a a fundamentally metaphysical kind of issue. It's something where, if we're lucky in the next, if we're really lucky, there'll be something that was already done 40 years ago that if you find the right experiment, you'll say, aha, this nails it. If we're less
right.
lucky, we'll have to, have some billion-dollar experiment that is created to try and resolve the question. But it's something that really is very much not in the metaphysical domain. I mean, it's very much a thing that you can really expect to interact with in actual physical experiments. I mean, it's a different question. What our perception of the universe is, and okay, computational irreducibility means things get to be very hard to predict. Yet, in our lives, our sort of existence depends on a certain degree of predictability. If everything was, with our finite minds, we sort of couldn't really coherently exist in a universe that was utterly unpredictable. And so what we are doing effectively is to find these sort of slices of computational reducibility in this otherwise completely sort of computationally irreducible behavior of the universe. And I think in a sense, the nature of science is to try and find those pieces of computational reducibility, those predictable things, those things about which one can have scientific laws. And I think perhaps a way to think about, I mean, when one thinks about the creation of form and things like that, there's sort of these questions of where are the other pockets of computational reducibility that allow a certain degree of predictability and in a sense comfort to kind of how things work. Where are those? And are those kind of different? Can one identify those different directions that are things like the idea of nesting in form? Are there things like that once we know them, it's like we then build a whole structure around them. And I think one thing to say, I'm sorry, I'm yakking on
No,
here, but the
it's okay.
the
No, my question was about the relationship between this computational irreducibility and also, let's say, the discrete nature of things on an ultimate level. And what's happening nowadays with neural networks, which in a sense seems to be indicating a kind of continuum or something which is more continuous, at least on a basic level, mathematically speaking.
Right. I mean,
Yeah, please.
right. So I mean, neural nets, as they're usually set up, have continuous weights. And that's important because when you train them, you say, you did slightly the wrong thing. Just move an infinitesimal amount in a different direction. And you get to use calculus to talk about how that works. That is not a necessary feature of neural nets. I didn't know that
Okay.
for sure until last year. But I tried to make some models in which one simplifies, 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 makes things discrete. There is a version, I could show some pictures. There's a version of a thing like neural nets that has the same kind of trainability as neural nets that is completely discrete. It is, in a sense, this is very unsurprising because let me give another example. I was studying years ago in the 80s, I was studying fluids. And usually people say, well, I'll take my continuous fluid and I'll approximate it with the numbers that computers can deal with. I'll discretize the fluid so that I can approximate it and so on. Um, and there, each real number represents some piece of some velocity field for the fluid, and you've packaged a lot of information about the fluid into all the digits of that real number. So what I did instead was to say, let's think about the fluid as being a bunch of extremely simple discrete molecules. And instead of packaging up a bunch of stuff into a single real number for a velocity field, let's distribute the information across a large number of very simple discrete molecules effectively. And so you're trading off, one big real number with 16 digits of precision or whatever, and 30, whatever it is, 60, 58 bits of precision in binary, so to speak. You're trading off this packaging of information into these approximate real numbers versus the sort of distributed representation of information in lots of discrete elements. And it's, in fluid dynamics, that works just fine. You can make a trade-off either way. It turns out the same is true with neural nets. That hasn't been, and in a sense, what happens is instead of making that little infinitesimal change to a real number, you're making you have a large number of degrees of freedom, a large number of bits, so to speak, and you're just changing a few bits, which is the same kind of thing as making a small change. In the mathematics, actually, you can even define Boolean derivatives and things like this. You can make mathematics that way. It turns out it's not. The much vaunted backpropagation method for dealing with neural nets doesn't really help so much in the discrete case, but it's very much the same idea. There's nothing. I didn't know it was going to work out that way. I mean, I had always assumed that it was important that you could sort of use calculus and have a continuous variation of weights, but it isn't. You can instead distribute that information across a large number of bits and just be changing a small number of bits. And it's actually very similar to what happens in the biological evolution case, to changing bits okay. So the difference is a little bit more technically. In the biological evolution case, it's like we have genomes that are small compared to the number of cells in our bodies. And so we're sort of changing the rule, and that then has a big downstream effect on how the rule works out. In what I've done with discrete machine learning, instead you have something like a cellular automaton where every cell in the cellular automaton, every cell in space-time in the whole cellular automaton pattern has a choice of, let's say, two possible rules. And so you're saying, okay, the way you learn the analog of the neural net weights is to say at each cell in the space-time pattern of a cellular automaton, at each cell pick rule A or rule B. And what you find out is then your learning is the pattern of A and B rules in this two-dimensional array. And it then works very similar to a neural net. Just as in a typical neural net, you have a series of layers and you're running the series of numbers through the sequence of layers. So similarly here, you're running the discrete bit pattern through this sequence of different kind of levels in the space-time pattern at which you have these different patterns of A and B rules and so on. So it's and we've taken to a certain distance in actually doing practical machine learning this way. It's an interesting technological issue because the technology of making purely discrete computation, Well, absent GPUs, which have taken floating point computation a long way, if GPUs didn't exist, then it would be a very clear thing that it's much more sensible to do things discretely if you can. Um, that we'll see what happens. There's a certain. I mean, this gets into the in today's world, people are putting a lot of emphasis on hundreds of billions of dollars of investment in the actual hardware of doing machine learning. Whether that is actually in the right direction or not, I think remains to be seen, because I think that the actual details of the hardware you need, in other words, people have this idea neural nets work. Okay, great. That's something that neural nets in their current form date from the 1940s. And yes, the big surprise is we managed to get them to do a bunch of things. I think to your points about universality, I think there is a lot more universality in the phenomenon of machine learning than than you might think. And that means that there is sufficient universality that doesn't matter whether you have this detailed pattern of a neural net with, multi-layer perceptrons in it, or whether you have this discrete cellular automaton pattern. The essence, the fundamental universal features of learning, so to speak, transcend these particular details of sort of the hardware implementation. And that's what I think we've already seen sort of anecdotally in some of the things that have happened in machine learning and in LLMs and so on. But my guess is that it goes a lot further than that. That there's a and that, for example, these we can. So what's the point of thinking about things discretely? Well, sort of at some level, if that's the way the world is built, it's useful to think about things in terms of the way the world is built. You could also argue that continuity is an important simplifying idea that we humans make a lot of use of. And so that's the reason why, if you can get continuity, it's wonderful. It isn't necessarily what what fundamentally exists. I mean, continuity, in a sense, the most fundamental continuity that we have is continuity in time of our experience. That is one of the most fundamental things we believe, is that we are somehow persistent in time. We are continuously moving through time. It's the same us an instant later as it is now, even though, in our modern theory of physics, we're made of different atoms of space at every successive moment of time. Yet we have this fundamental belief in the continuity of our existence through time. So I think, continuity is a very important simplifying assumption that we humans end up making. So it's not, when you can get continuity, grab onto it, so to speak. But there's a lot more richness in kind of the the way to think about the computational universe is, I think, in terms of discrete kinds of things. Most importantly, because sort of programs and data being the same kind of thing is very natural when things are discrete. It is not when things are continuous. One's never had a robust model of continuous computation. For continuous computation, it's always the program is very different in structure than the data it's operating on. And those things can be brought together when one's dealing with discrete systems. So a few thoughts about that. Gosh, you guys are bringing up so many interesting topics here.
Stephen, we've got Alberto has got a presentation on cellular automata and diffusion models. But first, I've got a question from Bavleen about Mathematica. Bavleen is from Mumbai in India, so we're spanning the world here.
Yeah. Hi, Stephen.
Hello.
I kind of had a lot of questions, but it got addressed with your conversation with Philippe just now. But I want to just prompt some thoughts and some ideas from the point of view of your platforms, right? Like Mathematica, Wolfram, and then Mathematica is almost like now 3 decades old, and it has built so many libraries, prompted so many fields to start using what you call a symbolic computation. Like one computation could be now seen not only in numbers, but once one could start to graphically see it, which maybe led many architects to start entering this field at a very early on stage. So I want to understand from your recollection of what prompted you to begin to share this and have this as a dissemination platform for your work, and where did it lead for you, and what should we learn moving forward with sharing of the work and knowledge, and how should one see the
Right.
world in the next years to come?
You know, I built Mathematica and so on because I wanted to have it to use myself.
Hmm.
It's pretty much as simple as that. I mean, but I'm a practical guy, so I know there are millions of other people for whom it's very useful. I mean, what has happened, I would say, is that the kind of the leaders of a huge number of fields have ended up sort of making use of Mathematica and Wolfram language as as a way to think computationally about their fields. I see computation as, the core paradigm of the 21st century. I mean, we've had, if we go back to the 17th century, the mathematical paradigm was the thing that got introduced at that time and that unlocked the possibility of exact science. What we now have in the 21st century is the computational paradigm, by which I mean basically thinking about things in terms of rules we can define and seeing what their consequences are. In mathematics, we have a particular set of rules that we think about. In computation, we have a broader set of rules. And, we have phenomena like computational irreducibility that mean that sort of that are generic features of what happens when we apply rules. But in terms of the way the way I like to think about what we've tried to do is to sort of make the world computable, so to speak, to have a computational way to think about things in the world. And that is something that, for example, in geometry, we've gone a long way now in dealing with kind of sort of representing shapes computationally. We actually did a thing a few years ago. Finally, we managed to make Euclid computational. It's taken 2,000 years, but finally you can actually describe, a set of constraints about circles and lines and so on, and you can sort of symbolically resolve those constraints. That's how that will relate to what happens with sort of more general computational geometry. That's an interesting future possibility. In other words, we've done planar geometry. We can solve planar geometry finally after all these years. We also have great ways to describe three-dimensional geometry and three-dimensional forms. I will say that I saw some Rhino stuff there. We've long had sort of connections to Rhino, but actually in the next version of Wolfram language, we will have all of those primitives available in a sort of fully computable way. So you'll be able to make those same kinds of geometric forms in a way so that you can compute things from them. I think in terms of I will say something about what's happened in science. And I don't know how that completely maps. So in science, people said, you want to make an exact model in science, write down a mathematical equation. That was before the 1600s. People didn't have a way to make exact models in science. People were just giving sort of philosophical arguments for how the world should work. Then one got kind of the mathematical paradigm and the idea of sort of writing down a mathematical equation to represent the world. Sort of the big thing that I started pushing in the 1980s was use programs as a way to describe what happens in the world. And there's been sort of a quiet revolution in most areas of science that when new models are made, they're usually made these days in terms of programs, not in terms of equations. And so how does that relate to the way one thinks about I don't know how that relates. I mean, I have to say, I think that the sort of, for example, imagine that, and there's sort of a pun here, in architecture, programs have a different meaning than they do in computation. The question would be, okay, so actually to say a couple of things here. So as you know, one question is, how do you describe the constraints, the things you are trying to achieve with some architectural form? There is potentially a language for describing those constraints. There is also a language for describing the way you create the form. And those, I think, the interesting interplay perhaps is between the language for creating the form, which might be something where the underlying rules from which the form is made are far beneath the sort of emergent actual form. And I think Philippe was showing examples where that was what was going on, where there was a sort of an underlying describable rule, but yet the full development of the form was something that sort of is irreducibly, there's sort of an irreducible process to go from that underlying description to the final form. And I guess one of the things I've been interested in recently is the description of constraints versus the description of the rules by which something is built. I mean, in science, there is, let's say in physics, there's typically a trade-off of explanations by mechanism and explanations by constraint. So, for example, in simple physics, the trajectory of a ball, some parabolic trajectory, you can describe that either in terms of the equations of motion of the ball. You say it was moving in this direction, and now at the next moment it will be moving in that direction. Or you can say there's a least action principle that says the trajectory taken by the ball will be the one that minimizes this quantity called the action. So there's an explanation by constraint, by in a sense by purpose, and there's an explanation by mechanism for what's going on. In biology, the explanation by purpose has been the dominant paradigm in evolutionary biology for the last 150 years. That this question of sort of how you think about explanation by mechanism in biology, that's a thing that I was recently working on and made a whole bunch of progress in. But I think it's an interesting question, perhaps, in thinking about architectural form and so on. You have a description in terms of purpose. I'm trying to make this building with such and such a program, as I understand your use of the term program, versus I'm trying to grow this building with rules that so I don't, I think there may be something rather interesting in the interplay between those ideas, because what we're finding in just to say in a very to Philippe's notion of universality, it's even more universal than you might imagine, in the sense that what has emerged in the last few years in my efforts has been that the foundations of physics, mathematics, biology, possibly economics, but that's still undetermined, and machine learning, that all of those fields have the same foundational idea. And the idea is the interplay between underlying computational irreducibility and the sort of computational boundedness and limitations of observers like us. So very simple example of that is fluid dynamics, where there's this sort of molecules bouncing around, this irreducible computational process, but yet our perception of it cannot trace all those molecules. And so our perception of it inevitably ends up being this continuum fluid interpretation. And it turns out that same interplay between the way we are as observers interacting with this sort of underlying computational irreducibility, that turns out to be, and this is something I never saw coming, the way that you get to derive general relativity, the theory of space-time, quantum mechanics, statistical mechanics, the possibility of doing higher level mathematics, the fact that biological evolution works, the fact that machine learning works. It's a very bizarre and very sort of it's a remarkable unification that all of those different things that seem to be quite different all end up being consequences of the same idea. So a question that one might have is, how does that idea apply in something like architecture? What I don't know. I haven't thought about this, but I've where again we have potentially the generation of form. Mostly in architecture, you don't, except in maybe Philippe's work and so on, we don't get sort of this really, we don't let the rules sort of play themselves out to generate really complex forms. We tend to stick with largely with simpler forms. And then, this question of sort of how does the how do we, how do we as the consumers of the architecture, so to speak, how do we interact with these kinds of things? I don't know the answer, but I suspect, I think there might be something rather interesting in that direction. I think it also relates to these questions about kind of the possibility of this kind of interconcept space and how that works and so on. I'm a little worried about the time here because I need to let some folks know that I am going to be late for something else. Hold on one second here.
And yeah, and I'll not step on what Alberto has been looking forward to discuss with you. But thank you so much for your answers. Yeah.
Sorry, I'm just excuse me 1 second because I'm just a second. I'm sorry, I just have to, I was expecting we would be long done by now, but this is great. And I want to continue with you guys, but I have to let some other folks know that I am going to be late.
You're a victim of your own popularity, Stephen.
Yes. Hold on 1 second here. Not okay. Hopefully. Good. All right. Please.
Yes. Okay. Alberto. Alberto's in Chile, I think.
Yes. Till the next week.
All over the world. Do you want to share your screen?
Oh yes, sure. I will try it now. Give me a second. So share screen. I think it should be this one. Share. So now I want to try to put my presentation here. Okay. I'm not sure if you can see. Yeah.
Yes. Yes.
Oh,
yes.
perfect. Yeah. Well, firstly, for me, it's an honor, as I'm Alberto Fernandez from Chile, but I'm actually working in the UCL, the Bartlett in London, and also University of Chile here. So I'm traveling quite a lot. Well, I must say something, but really important for me is just I just started to dig into the CA environment because of you. Because when I studied at the Bartlett more than 10 years ago in my master's, I just started with this it's a nice idea of what is a CA. For me, it was a surprise. I was a master's student at the moment, and then my tutor Alexander said at the moment suggests me to read your book, and but I never imagined to be here now after all this time, after all these years, to try to share what I'm trying to do with this in architecture, since that moment till now. Well, firstly, I started to understand, trying to create three-dimensional spaces using cellular automatas, using your rules, trying to understand how it's possible to create from 2D to 3D in a way, and then trying to create a three-dimensional space that, in a way, I'm even 3D printing sometimes. So as in this experiment that I'm actually showing you here. And but then I'm just trying to be brief because I know that we are just rushing a little bit. I just try to explore how to use the cellular automatas and artificial intelligence together in a way that trying to generate, or in particular using diffusion models, trying to bridge or trying to test in a way how it's possible to train diffusion models using artificial cellular automatas patterns. Yeah. Why? Because since a while I've been just receiving few comments from few colleagues saying in a way, but cellular automata is kind of old-fashioned. I said, really? Are you sure about that? Yes, everything has been done with this. Are you sure? So, well, in a way, that provocation has started to, in a way, to push me a little bit further to my the comfort zone in terms of what actually we were actually doing with modern architecture, discretization, and how it's possible to understand the construction elements or also architectural components in a CA environment. So in a way, this workflow, is kind of workflow, is trying to bridge the idea of architectural components, CA classes, and then how to create a kind of AI translation, and then getting three-dimensional information, and then going to fabrication. That's the idea behind. And so AI in architecture is something I'm quoting something that Neil wrote time ago. And but basically is trying to understand the integration of artificial intelligence, machine learning, and in a kind of particular workflow. And this workflow is about the idea of CA plus diffusion models. So in a way, I started to think about what is for a diffusion model the prompt or the idea of the concept of cellular automata and architecture, because you don't know, because someone trained this, and we don't know what exactly is going on inside of this model. So I just started with this kind of tiny model, the diffusion model 1.5, and then I asked the idea, what is a cellular for this model? And I started to get this kind of examples, images that were actually generated using a diffusion model. Then I asked about cellular automatas, and the diffusion model started to think about, okay, what I can do with this prompt. And these were the few of the results. So then I added the other idea, plus architecture. And then it became even more kind of weird in a way, because we can read an idea, kind of patterns coming from automatas, but with a weird mix of architecture in a way, but we don't know yet what is actually going on. So I started with this next step, which is based on, okay, what if, let's try to train something using CA patterns, trying to kind of push a little further this idea of diffusion model, and a diffusion model being trained with our genetic data, plus something more specific like that. So, well, I started with, okay, let's use LoRa models. So I started to ask to sorry, I think I'm not sure if it's working. Yes, it's working. And so I used few CA examples that I actually create using asynchronous CAs based on Chris Langton. And then from these patterns, I started to get information, and from this information, finally, I get I built a database without with hundreds of images, just hundreds and hundreds and hundreds of images for sure. You should do it in that way. And then okay, I asked to the model about what the model can see. So in a way, the model started to see few interesting concepts, like, okay, I can see this this thing from this image, I can see these other things from these other images, and then finally, I got a kind of database with one with images, another way on the other ones or just with concepts, and then finally, after all this process, because it's really interesting, because you never know what is actually seeing the machine based on the images you're actually asking, yeah, because you're asking to the machine what is the real meaning of this image. So then I create my LoRa models using all this information. I just create 4 for this example, and then I said, okay, let's try what is going to happen finally. And then I got this first weird image. I said, oh, this is interesting, because this is something that is not coming from the original CA. It's not coming from the original diffusion model. It's something else. So that's something else. For instance, where these were the results. from this example or this database, I got this set of images, and I said, okay, this is a kind of hybridation between what is actually happening from the CA plus the diffusion model, and then it's becoming more organic in a way, but actually is artificial. It's something that is discrete, but based on the resolution based on this actually information. And well, in more detail, if these were just super tiny images, just 512 by 512, not even 1000, no, just quite tiny. But then the questions were really interesting because I said, okay, what is the next step? Because I'm just saying, okay, I have a CA, I have a diffusion model, but I need to introduce the architectural idea behind. Yeah. So firstly, I trained more and more and more, trying to get more and more patterns, more and more samples. Few samples were even were getting few kind of color information from black and white, and then from red or things like that. And then I can read some few things that are okay, this looks like a CA, but not. But in a way, I know that it's coming from the hybridation from the CA plus the diffusion model. So few others were more like landscape-based or more like cells proper artificial life in a way. Were really fascinating in terms of the information that is started to emerge from this process. But then I'm going to accelerate a little bit. I started to understand. Well, let's try to see what is actually is possible to get as information from the architectural space, as I said before. So these ones were basically closer to the idea of architecture in a way because they look like facades in a way, like towers or things like that. But finally, after all, I started to think about what's possible to do with this. So I said, okay, let's try to hybridize this a little bit more. So I got facades in one side, and then I forced the idea of a CA AI translation using these architectural examples, crossing the information, forcing this CA AI model as a kind of translator over these samples, and then I got the deep map information, and finally 3D models, which in a way is asking or is opening the agenda for a question that I have for you, and something with this we can start to talk a little bit. Is this a new kind of architecture or not? So this is something very interesting that I want to talk with you now.
Well,
thank you.
I mean, that's an interesting, cool idea to train a diffusion model on cellular automaton images. Maybe I should show before we wrap up. I should just show a few pictures of things. Maybe you can let me share for a second, and just let me see. Here we go. So just the few of the things I was mentioning, I just show some pictures of them. So this is the kind of interconcept space. This is what I was calling cat island. This is things close to a cat. These are kind of interconcept spaces, right? So this is something that's trained from, a billion human images, right? As opposed to being trained from things like cellular automata. Now, I actually also looked at let's see. I am here we go. I actually have trained some okay, so if we have a cellular automaton image like this, then train a transformer model, autoregressive model, and then you say, okay, predict what happens in the cellular automaton image. When the cellular automaton image is periodic, it does pretty well. When it's more complicated, that's something closer to the kind of thing that I think you're seeing, where this is the neural net prediction of something that's a bit like the cellular automaton, but it is generalized. It is kind of almost the human processed. And I say human in a generalized sense, because the neural net isn't really a human, but it's kind of human-like processing of what do we get out of that image. Well, this is feeding back sort of the what do we get out of the image type of thing. So I think, I mean, this is you've looks like you've gone very nicely further than this. This is just something where I was looking at what happens. Well, I had different reasons to do this, but what happens. I think this is successive training steps. Looking at that. So that's one set of comments. In terms of the evolution, let me just show something here. Yeah, so this is I was mentioning biological evolution. This is that's an underlying rule. This is starting off from a single red cell. That's what this particular rule does. Then the idea is you make mutations in that rule. You're changing single bits in the rule, and you're asking what effect does that have? So here, for example, it's showing the fitness function is how long does the pattern last? And what you're seeing is as you change the rule, you occasionally have these breakthroughs where the pattern lasts longer, and you end up with these different sequences. Different sequences of possible. Oh, that wasn't a good idea. Sorry. These different sequences of possible patterns. In a sense, each one of these is a different idea about how to live a long time. And so, this is kind of a way of generating form. I mean, in the particular thing I was looking at, the models are simple enough. You can trace out all possible ways that you can make mutations, all possible forms you can get. I think one thing you might find interesting, I did look at what is this? This is different forms of different aspect ratios and so on. Let me see if I've got a picture of this. I think I might have. Here we go. This is two-dimensional cellular automata. So this is looking at this is a succession of more fit, longer-lived two-dimensional forms. You can see the same. I think these are a few examples. These are a few examples of winning two-dimensional forms that in this particular case, the fitness function is live a long time and then die out. I mean, one thing I find interesting about these is, occasionally there's a bit of explainability in what's going on. Most of the time, the structure is it just does what it does, and it's not really explainable. But so that might be sort of a version of I mean, this question, I think, of the interplay between the constraint you put on the system and the form that you get out, I think is interesting. By the way, just to talk about, let's see, this is in discrete machine learning. Let me see. I'm just showing. Well, this is kind of standard continuous machine learning. You're learning that particular function at the bottom of the page. Those are neural nets. But now you can do the same kind of thing with just a purely discrete system where you are filling in sort of different rules, rule A or rule B at every step. And then you're using that as your processor of the input information. And you can make this was just in response, I suppose, to an earlier question about discreteness and the importance of discreteness is whether you can have continuity and whether continuity is important for sort of the idea of machine learning. But in terms of I mean, this interplay between let's see, I think I might have another picture that might be of interest here. Let's see. See if I can pull this up. Yeah, so what's the interplay between, let's say, stable diffusion and things like cellular automata? And so, if we just look at whole collection of images, we can look at their color, their distribution in color space. We could say, here's a very simple average image, right? Not very exciting. But now, when we think about what is Stable Diffusion doing, what it's doing is, let's see if I have a good picture here. Maybe this is a picture. It's going from noise to some kind of attractor that, in the case I think you were showing with clip, for example, is something that meets certain clip constraints, right? You're evolving towards a thing that is clip successful, so to speak. But what's happening is there are, in general, many, if we think about it in terms of cellular automata, there are many attractors that are sort of clip successful. Depends on what initial conditions we have, depends on what randomness we throw in initially. But what we're going to get in this particular case, the sort of successful things are always things which are just these vertical stripes, right? And so this is saying, this is the randomness you put into the diffusion model. This is now, in this particular case, we're not applying the kind of stable diffusion algorithm, which is getting us these attractors, the A attractor or the B attractor. Instead, we're applying a cellular automaton rule to take us towards an attractor. The attractor, there are many pieces to that attractor. We could have any collection of stripes here. So I think that's sort of the way to think about it. I mean, I think this is showing, what is this showing? This is showing how, as a function of, I now forget exactly what this is, but maybe this is an example here. This is showing these are basically what we're saying is, the analogy is the different possible attractors for the cellular automaton are like the things that clip says are meaningful, where for you, meaningful means they're kind of like a cellular automaton pattern. For traditional stable diffusion, mid-journey, whatever, it's like a picture that somebody had as a photograph or something. And so I think what you're kind of saying, what you're doing is you're saying, what does a picture like a cellular automaton, what does it mean like a cellular automaton? Well, you're saying, I'm going to use a neural net, kind of human-like perception to decide when the picture is like a cellular automaton picture, which is an interesting thing to do. I mean, and then you're asking, when you have with that notion of similarity, when similarity is based on neural net similarity, so to speak, what do you grow that is kind of just as I was showing Cat Island for pictures of cats, you're asking, what is cellular automaton island like? And what's on the periphery of cellular automaton island that is, from the purposes of the sort of human-like perception, is similar to a cellular automaton, but is not a cellular automaton. I think it's a reasonable, I don't know. Okay, my prejudice would be that what you will see, that you are kind of venturing into concept space. And that when you get far into concept space, you could as well be just using different underlying rules. That is, the fact that you are using, what your kind of mechanism, what your workflow, I think, is giving you is a way to say, stay close to, the core cellular automaton thing is in a sense quite alien to us. It's a thing sort of plucked out of the computational universe. And now you're saying, let's stay fairly near that thing that we plucked out of the computational universe. But as we go further away from the thing that we had identified, we're going out into the wilds of the computational universe, so to speak. So I'm not sure, in a sense, what you might think, which I think is what the interesting possibility is, can you humanize things in the computational universe by using the fact that you have this this neural net sort of humanizing kind of structure there? I think that's an interesting question. I mean, to me, if I look at let's see, where is this? Yeah, I mean, if I'm out in in sort of the wilds of interconcept space, just based on ordinary images, not cellular automaton images, there is a question of what makes it make this reticular kind of structure. I don't know. Nobody knows. I can say with considerable confidence that nobody knows why that happens. But it is interesting that even when it's trained from our traditional, inventory of images, photographs or whatever else, that even then, in the interconcept space of such a system, you're getting these kind of reticular types of things. I don't know why. I mean, I think that, and from a cellular automaton, you say, well, it's following the lead of the cellular automaton, but that's not what's happening here because there was no, and I think, yeah, I mean, it's a wonderful area. There's so much to figure out, and it's cool that you've started with sort of learning from the space of cellular automaton patterns. I mean, the challenge there is that those patterns are themselves already alien to us, so to speak. And so it's but I think in the three dimensionality and so on, an interesting thing to do, it seems to me, would be you can certainly formulate this whole stable diffusion structure for voxels in 3D images. I will say that in Wolfram Language we deal with 3D images in a very lovely way, so it's technically easy to do. I have never seen anybody do that of kind of growing and that would be, I think, an interesting thing to try to do is to sort of make use of. I don't know, how do you generalize when the training data is a little different? I mean, you could use three-dimensional cellular automata to train the thing. Actually, that would be an interesting thing to do. I mean, if I were to take
definitely
I mean, if in how do I have a nice example? Well, I'm sure it's easy enough in Wolfram Language to generate. I'm trying to think. I had used them for something recently, and I had a bunch of very lovely 3D cellular automata. But you get these very interesting forms, and one could imagine sort of generalizing from those using a diffusion model. I think that will make something interesting. That will be my guess. It's
yeah, you're right. Oh, thank you very much. You're really an amazing person. You're sharing all your images online for all of us. Thank you very much for
Thanks. But by the way, I will make the practical point for anybody who's actually interested in following up on these things. If you look at my writings website and so on, I've written about lots of kinds of things. Every one of the pictures and everything I write, you can click the picture, you will get Wolfram Language code. Unless something went horribly wrong, when you run that code, you will get the picture. So it's a good place to start. The only thing, those pictures of cats, they need a GPU. But most of these things are simpler.
Oh, amazing.
Anyway, but it was great to see you work, and it's great. I'm really really excited. Oh wow, there's a smaller morel as well. A nested collection of morels.
We one final question about interconcept space from a philosopher. I just think, have you got time for that? A short question?
Sure.
Okay.
Yes,
Sonia Diego, or Dr. Sonia Diego, just finished her PhD. Sonia.
Thank you so much.
What are your big fans?
Yeah, we're all big fans here. Can you hear me okay?
Yes, I can.
Thank you. No, yeah, I was thinking your concept of interconcept space, which has been super useful. Thank you very much for that. Is actually really well represented by the ancient Chinese logicians, the school of names, who had this dictum that white horses are not horses. So if you have, of course, the concept of white horse, that's not the concept of horse, right? And you have everything in between. Yeah, just had to think of that.
I didn't know about that. I should look that up. I don't know about that.
Yeah, it's super interesting, the work done there. It's like predating Wittgenstein by thousands of years, basically. So really fun. But no, I have a million questions, but I'll try to make it short in the interest of time. So kind of coarse graining with concepts creates continuity between minds, right? So we can think maybe then of some sort of atomic or discrete nature to concepts, but that would be
I agree.
Yeah,
to say in my version of that would be the following thing. In our brains, we have all kinds of neuron firings that are happening, but in order to communicate to your brain, from my brain to your brain, we have to kind of have a packaged version of what is going on. And we take all of those neuron firings and we kind of concentrate them down onto this discrete thing that we call a concept that happens to be often represented by a word in human language. And then, I can say that word, and then when you unpack it in your brain, you get something that is some kind of echo of the pattern of neural activity in my brain. So I agree. I think that to me, concepts are the analog of particles. So in physical space, motion is something which in our models of physics we have to derive. It's not obvious that a thing could be moved and still be the same thing. That's something that has to be derived. And the things that are the carriers of pure motion in physics are particles like electrons. An electron is a thing that stays as an electron even though you move it to somewhere else. And it is an interesting fact that there is a discrete collection of such things that we identify in physics. So I think that in what I end up calling rulal space, the space of all possible kinds of ways of interpreting the world, that the analog of particles in rulal space is concepts. The concepts are the discrete packagings that have the property that they can be translated from one mind, one set of rules about how the world works, to another set of rules about how the world works. And that, in a sense, concepts are the robust thing that can undergo pure motion in that space of possible minds. At least that's my current interpretation of how that works.
Can I ask you a really quick follow-up question in that sense? What do you think about compression then, at least in our current computational paradigm? So do aspects of what we understand about compression today maybe hold some promise for understanding aspects about the evolution of space-time as kind of an explorative network we'll describe.
Right. I mean, look, the big thing about folks, observers, critters like us, is we get data in, a gigabyte a second or something. But yet what we do happens at, 10 decisions per second or something. We are hugely compressive of our experience of the world. And I think I've increasingly come to believe that the essence of the thing that we identify as consciousness is this phenomenon that we are abstracting this sort of single thread of experience from all of this detail of what's coming into our senses, and that there's lots of actual structures, physiological structures in the brain that are trying to go from all of this data coming from the outside to the thin thread of decisions that we make and so I think that somehow I mean, I think compression in that sense is critical to our experience of the world. I think were we, if we say, I mean, it's a little disappointing that this sort of vaunted idea of consciousness that we're all very proud of is something which is actually a simplification. It is not, the physical world is doing computation in a much more general way, in a sense, than the particular thing that we're doing of taking this huge amount of sensory data and turning it into a small thread of decisions. And I think that's so I mean yes, I think it's one question is, when you take the complexity of the world and turn it into a small thread of decisions, are there laws about how that works? That is it the case that you can, when you make that thread of decisions, that you can make that thread of decisions in a way that does not require huge amounts of computation? In other words, that you can simplify the world, that the part of the world that you're sampling can be described in a simple enough way that you can deal with it with a finite mind. And I think that's in a sense, we are selecting from the complexity of the world these slices of simplicity that allow us to basically make sense of the world. And those slices of simplicity turn out to be the things that we call the laws of physics and things like this. And the thing that's, as I was mentioning, the thing I think is kind of super exciting, I completely did not see coming, is that given what we know about what we are like as observers of the world, it is inevitable that we have to observe the laws of physics that we observe. In other words, that those laws of physics they are contingent on being observers like us, but they are inevitable for observers like us. They are derivable because of our nature as observers of the kind that we are.
Thank you. Yeah, I have a lot more questions, but we don't have time.
Okay, there is I just want to say that in terms of there's such a rich set of things that I think I feel like we are very close to, some things I feel like we've managed to understand sort of what has been previously talked about purely in terms of philosophy. We're sort of getting a scientific understanding of those things, but I think there's just a incredibly rich collection of things, and I do want to hear about somebody can send me the pointer to the ancient Chinese philosophers, because I don't know about that, and I'd like to know about that. But I think there's an infinite number of connections to be made, most of which I've not been able to make. And I'm super late for something else, even though you guys are talking about such interesting things.
I've got to say one thing, and I want to ask Sonia. You claim you didn't want to be a philosopher. I heard a philosopher, someone speculating today at a generic level. I don't know whether Sonia is a philosopher of artificial intelligence. That's what I came across. A lot of these, I mean, I think it is a kind of philosophy. It's emerging in a kind of Wittgensteinian way out of the world of science and technology. But it is a kind of a conceptual map of the world, which I think is enormously enriching.
Right. I mean, look, the thing that in my own kind of methodology for doing things, I've been sort of, in a sense, the things I do are a mixture of philosophical type thinking together with a big tool, which you guys are also, using, which is computer experiments. That's something we just haven't had before. In other words, we've been able to do these slow, laborious experiments in the physical world. Now, the thing that's super powerful is, the sort of very easy. I mean, okay, I've spent decades trying to make it easy to do computer experiments. It now is very easy to do lots of computer experiments. They give us, they are the sort of raw material, the empirical raw material from which we can make philosophical conclusions. And I think it's sort of an emerging thing, and so despite my efforts as a kid, I sort of have become a little bit of a philosopher, but so it goes. Let's see. My children will make similar statements about my children have made statements about they'll never do things like the kinds of things I do, and it turns out that they do. So it just works that way.
No, but I would say one thing out of the 1930s, when the time when I guess your grandparents would have left Germany, the concept of the model of mimesis in Benjamin and Adorno is now very, very close to what I understand the notion of the model and modeling in computation. I do think there's something in this notion of compression you were talking about, and that needs to be taken further and teased out. To be continued.
Yes, a lot of very lovely questions and thoughts and so on. Anyway, I'm excited to see what you guys are doing, and I'm now very curious what all the rest of you do. But maybe another time.
I'm going to send you a copy of this book, and I'm going to recommend anyone this book on what is ChatGPT doing. Stephen, this has been fantastic. Thank you so much. It's very generous of you on a Sunday afternoon to come do this, and I think your fans are so grateful. Amazing. So thank you for your contributions over the years. They've been so important to architecture, and thank you so much for your contribution today. It's been wonderful. Thank you.
Great.
Thank you.
Very nice to meet you guys.
Okay.